Hello friends, in the earlier lecture we discussed in length about how magnetic field is defined with the help of a test charge moving through a magnetic field with a particular velocity, learnt about magnetic field lines, discussed the right hand rule and finally talked about Hall effect. In today's lecture, we shall be talking about how a charged particle behaves when moving through a uniform magnetic field and find out the magnetic force on a current carrying wire. If a particle moves in a circle at constant speed, we can be sure that the net force acting on the particle is constant in magnitude and points towards the center of the circle, always perpendicular to the particle's velocity. Think of a stone tied to a string and rotated in a circle on a smooth horizontal surface, or of a satellite moving in a circular orbit around Earth. In the first case, the tension in the string provides the necessary force and centripetal acceleration. In the second case, Earth's gravitational attraction provides the force and acceleration. In both the cases, and even in the case of a charged particle, we would like to determine the parameters that characterize the circular motion of these particles or of any particle of charge magnitude q and mass m moving perpendicular to a uniform magnetic field at speed v. We earlier found that the magnetic force acting on a charged particle moving in a magnetic field is perpendicular to the particle's velocity, and consequently the work done by the magnetic force on the particle is zero. Now consider the special case of a positively charged particle moving in a uniform magnetic field with the initial velocity vector of the particle perpendicular to the field. Let's assume the direction of the magnetic field is in the page as in figure. As the particle changes the direction of its velocity in response to the magnetic force remains perpendicular to the velocity. As we know, if the force is always perpendicular to the velocity, the path of the particle is a circle. Figure shows the particle moving in a circle in a plane perpendicular to the magnetic field. Although magnetism and magnetic forces may be new and unfamiliar to you now, we see a magnetic effect that results in something with which we are familiar, the particle in uniform circular motion. The particle moves in a circle because the magnetic force is perpendicular to the particle's velocity and magnetic field and has a constant magnitude qvb. As figure illustrates, the rotation is counterclockwise for a positive charge in a magnetic field directed into the page. If q were negative, the rotation would be clockwise. We use the particle under a net force model to write Newton's second law for the particle as Fb is equal to ma. Because the particle moves in a circle, we also model it as a particle in uniform circular motion, and we replace the acceleration with centripetal acceleration, that is Fb is equal to qvb, which is equal to mv square upon r. This expression leads to the following equation for the radius of the circular path, that is r is equal to mv upon q into b. That is, the radius of the path is proportional to the linear momentum mv of the particle and inversely proportional to the magnitude of the charge on the particle and to the magnitude of the magnetic field. The angular speed of the particle is then omega is equal to v upon r, which is equal to qb upon m. The period of the motion is equal to the circumference of the circle divided by the speed of the particle, that is t is equal to 2 pi r upon v, which is equal to 2 pi upon omega, which is again equal to 2 pi m upon q into b. These results show that the angular speed of the particle and the period of the circular motion do not depend on the speed of the particle or on the radius of the orbit. The angular speed is often referred to as the cyclotron frequency because charged particles circulate at this angular frequency in the type of accelerator called a cyclotron. Cyclotrons, beams of high energy particles such as high energy electrons and protons have been enormously useful in probing atoms and nuclei to reveal the fundamental structure of matter. Such beams were instrumental in the discovery that atomic nuclei consists of protons and neutrons, in the discovery that protons and neutrons consist of quarks and gluons. Because electrons and protons are charged, they can be accelerated to the required high energy if they move through large potential differences. The required acceleration distance is reasonable for electrons because of their low mass, but unreasonable for protons because of their greater mass. A clever solution to this problem is first to let protons and other massive particles move through a modest potential difference so that they gain a modest amount of energy, and then use a magnetic field to cause them to circle back and move through a modest potential difference again. If this procedure is repeated thousands of times, the particle ends up with a very large energy. Here we discuss an accelerator that employ a magnetic field to repeatedly bring particles back to an accelerating region where they gain more and more energy until they finally emerge as a high energy beam. Figure here shows a cyclotron in which the particles, say protons, circulate. The two hollow D-shaped objects are made of sheet copper. These Ds, as they are called, are part of an electrical oscillator that alternates the electric potential difference across the gap between the Ds. The electrical signs of the Ds are alternated so that the electric field in the gap alternates in direction, first towards one D and then towards the other D, back and forth. The Ds are immersed in a large magnetic field directed as shown. The magnitude B of this field is set via a control on the electromagnet producing the field. Suppose that a proton injected by source P at the center of the cyclotron initially moves towards a negatively charged D. It will accelerate towards this D and enter it. Once inside, it is shielded from electric field by the copper walls of the D. That is, the electric field does not enter the D. The magnetic field, however, is not screened by the copper D. So the proton moves in a circular path whose radius, which depends on its speed, is given by r is equal to mv upon q into b. Let us assume that at the instant the proton emerges into the center gap from the first D, the potential difference between the D is reversed. Thus, the proton again faces a negatively charged D and is again accelerated. This process continues, the circulating proton always being in step with the oscillations of the D potential until the proton has spiraled out of the edge of the D system. Magnetic force on a current carrying wire. We have already seen, in connection with the Hall effect, that a magnetic field exerts a sideways force on electrons moving in a wire. This force must then be transmitted to the wire itself because the conduction electrons cannot escape sideways out of the wire. In the figure shown, a vertical wire carrying no current and fixed in place at both ends extends through the gap between the vertical pole faces of a magnet. The magnetic field between the faces is directed outward from the page. In figure B, a current is sent upward through the wire. The wire deflects to the right. In figure C, we reverse the direction of the current and the wire deflects to the left. And this figure shows what happens inside the wire of previous figure B. We see one of the conduction electrons drifting downward with an assumed drift speed Vt. The equation Fb is equal to Qv b sin phi, in which we must put phi is equal to 90 degree, tells us that a magnetic force of magnitude E Vd into B must act on each such electron. From equation Fb is equal to Qv into B, we see that this force must be directed to the right. We expect then that the wire as a whole will experience a force to the right. If, as was shown inside the wire, we were to reverse either the direction of the magnetic field or the direction of the current, the force on the wire would reverse, being directed now to the left. Note too that it does not matter whether we consider negative charges drifting downwards in the wire or positive charges drifting upward, the direction of the deflecting force on the wire is the same. We are safe then in dealing with a current of positive charge as we usually do in dealing with circuits. Consider a length L of the wire in figure. All the conduction electrons in this section of the wire will drift past plane XX in a time t is equal to L upon Vd. Thus, in that time, a charge given by Q is equal to It is equal to I into L upon Vd will pass through that plane. Substituting this into equation A yields Fb is equal to Q Vd into B sin phi, which is equal to IL upon Vd into Vd B sin 90 degrees. So Fb is equal to ILB. Note that this equation gives the magnetic force that acts on a length L of straight wire carrying a current I and immersed in a uniform magnetic field B that is perpendicular to the wire. If the magnetic field is not perpendicular to the wire, the magnetic force is given by a generalization of equation C as Fb is equal to IL into B. Here L is a length vector and is directed along the wire segment in the direction of the conventional current. The force magnitude is then Fb is equal to IL B sin phi. Here phi is the angle between the directions of length vector and magnetic field. Torque on a current loop. Much of the world's work is done by electric motors. The forces behind this work are the magnetic forces that we studied in the preceding section, that is, the forces that a magnetic field exerts on a wire that carries a current. The figure here shows a simple motor consisting of a single current carrying loop immersed in a magnetic field. The two magnetic forces and acting in opposite direction produce a torque on the loop tending to rotate it about its central axis. Although many essential details have been omitted, the figure does suggest how the action of a magnetic field on a current loop produces rotatory motion. Let us analyze that action. This figure here shows a rectangular loop of sides A and B carrying a current through uniform magnetic field. We place the loop in the field so that its long sides labeled 1 and 3 are perpendicular to the field direction, but its short sides labeled 2 and 4 are not. Wires to lead the current into and out of the loop are needed, but for simplicity are not shown. To define the orientation of the loop in the magnetic field, we use a normal vector that is perpendicular to the plane of the loop. This figure shows a right-hand rule for finding the direction of normal vector. The extended thumb then points in the direction of the normal vector. In this figure, the normal vector of the loop is shown at an arbitrary angle theta to the direction of the magnetic field. We wish to find the net force and net torque acting on the loop in this orientation. The net force on the loop is the vector sum of the forces acting on its four sides. For side 2, the length vector in equation D points in the direction of the current and has magnitude B. The angle between length vector and magnetic field for side 2 is 90 degrees minus theta. Thus, the magnitude of the force acting on this side is F2 is equal to IB into B sine 90 degrees minus theta, which is equal to IB into B cos theta. We can show that the force vector F4 acting on side 4 has the same magnitude as F2 but the opposite direction. Thus, vectors F2 and F4 cancel out exactly. Their net force is 0, and because their common line of action is through the center of the loop, their net torque is also 0. The situation is different for sides 1 and 3. For them, the length vector is perpendicular to magnetic field. So the forces vectors F1 and F3 have the common magnitude IAB. Because these two forces have opposite directions, they do not tend to move the loop up or down. However, these two forces do not share the same line of action, so they do produce a net torque. The torque tends to rotate the loop so as to align its normal vector with the direction of the magnetic field. That torque has moment arm B upon 2 into sine theta about the central axis of the loop. The magnitude of the torque due to forces vector F1 and F3 is then given by this equation. The magnetic dipole moment. As we have just discussed, a torque acts to rotate a current carrying coil placed in a magnetic field. In that sense, the coil behaves like a bar magnet placed in the magnetic field. Thus, like a bar magnet, a current carrying coil is said to be a magnetic dipole. Moreover, to account for the torque on the coil due to the magnetic field, we assign a magnetic dipole moment to the coil. The direction of the magnetic dipole moment is that of the normal vector to the plane of the coil and thus is given by the same right hand rule. That is, grasp the coil with the fingers of your right hand in the direction of the current such that the outstretched thumb of that hand gives the direction of magnetic dipole moment. The magnitude of magnetic dipole moment is given by mu is equal to NIA. Here N is the number of turns in the coil, I is the current through the coil, and A is the area enclosed by each turn of the coil. Conclusion: a straight wire carrying a current I in a uniform magnetic field experiences a sideways force. A coil of area A and N turns carrying current I in a uniform magnetic field will experience a torque which is equal to the product of magnetic dipole moment of the coil and magnetic field. So friends, that is it for today. See you in the next lecture with more on magnetostatics. Thank you very much.